Okay, so first of all, I want to start off by talking about, let's go back to the one variable case, the kind in like high school calculus, I guess you could consider it. So what we would do then is this integral, something like this, the integral from a to b of f of x dx. And what the graph would look like is something like this. So you have your x and y axis, right? And then A and B lie on the x-axis, so like A's here, B's there, A and B. And then you have some function going along, some curve, right? So this is our f of x. And then A and B, this is our intervals here. Hold on. This is my attempt at dotted lines. Okay, yeah, and sadly this isn't much better in real life either. So, and what this integral gives us is actually the area under the curve, right? So it would be this area right under here from A to B. So what this gives us is, and this is the signed area, it's called signed area. Because if you were to have some curve that goes above and below, like the sine graph, right, this is a positive area. It's considered positive, even though, I mean, area is always positive technically, kind of like distance, but the way we consider this, anything that falls below would be negative, right? So signed area, so that means it could be positive or negative. Okay, so that was the one-dimensional case, and we're all pretty familiar with that, hopefully. And now what we're going to be doing is integrating with two variables. So, oh, one more thing I would like to point out with this first case here, is that our a to b, our interval here, so x being going from a to b, this interval is, it's kind of like our domain, I guess you could consider it. I don't know if you remember, I think we probably even go over this in all the way back to algebra and stuff, but domain was like our x range, sort of, like where the x values could lie. And then our y's were, the possible y values were considered the range. So anyways, that's where domain comes in. And now let's switch into two variables. So now we're going to have something called a double integral, because for each variable you add, you basically add another little integral sign. Integrand. No, that's not the integrand. I don't know. Whatever the name for the symbol is called, I'm just going to call it double integral. And that is going to be over D, and this represents our domain. Okay, domain. But this time, since we have two variables, the domain is going to be a bit more complicated than just one interval on the x-axis. So here we have the domain, and then the next part, f of x comma y. So now we're going to have a function of both x and y, and then dA. This is our differential, and dA here is represented by dx times dy, and those could always be switched, like dy dx. Okay, so let me rewrite this. So now what we're actually going to have, this is what we're going to start with, is something like, we have to have bounds for these two integral signs, right? So what I'm going to do is write c to d for this one, and a to b for this one, okay? And then we have our normal f of x comma y, and then we'll make this dx dy. Okay, so what this means is that okay, so for double integral, and eventually we'll move on to triple integrals. Yeah, those are fun as they sound. So what's important here is that the dx matches up with its bounds, and the dy matches up with its bounds, or its interval. And the way you tell is the outer ones correspond to each other. So y, we know that y, the interval for that is going to be from c to d, because that's on the outer. And then the inner is a and b, and that corresponds with our dx. So x is going to be from a to b. All right. So, yeah, so what this tells us is that what we're actually going to have is something, okay, I'll write it on the next slide so I can draw out a picture of it. So here we have our double integral, and I'll just write d down here for now. Function of x and y, dA. So before we had our domain in the one-dimensional case, the very first thing I showed you was x goes from A to B, and that was it, right? The domain existed on the x-axis, and that was all. But now with this double integral, our domain is actually going to exist in 2 dimensions in the xy plane. So here's xy. So we kind of just like laid it flat on the floor. And now we have this other one, this other axis called z. So this transforms it into a 3-dimensional space. However, so D is somewhere down here. I'm just going to write, well, we're starting off with a simple case. Okay, that was a really bad line. Hold on. Okay, that was pretty good. We're starting off with a very simple case of the double integral, and we're integrating over some kind of rectangular box. Okay, so what this tells us, here's, remember, I'll write out this. So we have from C to D, and then from A to B, and then we have our whatever function this is. This could be something like, just for example, it's like x times y. They'll give this to you in your problems. And then this is dx, dy. Okay, so we said x goes from A to B. So x going on the x-axis, this is A, and this is B. And then y goes from C to D. So here's C, and here's D. All right. So actually what we have is our domain is this part here. This little, it looks like a square, or it could be a rectangle, whatever. And then where the f of xy comes in is this is some surface, some z determined by this function. Okay, so if you had xy or something, it would look like, I actually don't know what it would look like exactly because I'm not an expert at graphing 3-dimensional things. But anyways, so what you're going to have is some point in here, and then you're going to have some kind of surface floating up in the air in 3-dimensional space. Okay, so it's going to look something like that. And really, this might get a little bit confusing with the lines, but you can kind of see it's like a surface. I think of it like a blanket, kind of, just floating up there. Or even a magic carpet. That works too. So, anyways, so what this does, this integral here, so we're going to draw lines going straight up, kind of. Please excuse the drawing. It's kind of really hard to do, well, on paper, first of all, and it's even harder to do with a stylus, pad, and pen. But anyways, you get the idea. So drawing straight lines up from the domain, we're going to get something that touches the carpet. I'll just call it the carpet. So here it touches, and this is our domain down here. This little shaded thing, the shaded square is D. All right, that's determined by our interval on x and interval on y. So anyways, the point that I'm trying to make is that this whole integral, this double integral here, and which is equal to the one here, this is going to give us, our answer is going to be the signed, so it could be positive or negative, volume. And in this case, the signed volume under the carpet, or the curve, going up, which is actually, which exists in 3D space. It's kind of hard to conceptualize, but this is kind of the idea behind it. Okay, so this is going to be a signed volume, and this is your double integral. Okay, so I'll start on the next topic on the next slide. Alright, so again, I'm going to draw a quick sketch of what I just did, kind of. Okay, something like this. Then we have, just a warning, all of my surfaces are probably going to look like magic carpets, just because it's easier for me. And you'll find that it might be easier for you as well when you do problems in homework. So, okay, I shouldn't have drawn that line. Hold on one moment. So here we have our C to D for Y, right? And then if we extend these down, this is going from A to B on X. Okay, so what we have, draw my line straight up, little dotted line, straight up, okay, little light lines. Okay, so let's say it crosses here and here. This is where it's touching the graph, the carpet, okay, when you go straight up. All right, that was actually pretty good. So, the first thing that as I said before, we're starting with the simplest, which is a rectangular domain. Domain. And we said that the x interval is from a to b, and our y interval is now from c to d. Okay. And what this looks like on the xy plane, I'll lay it down here. So here's our x and here's our y. I'm drawing whatever's on the floor, basically. So we have our a and b and c and d. So here's c, here's d, here's a, and here's b. So we're looking basically in this little rectangle. Okay. So for here, now I'm going to introduce the Riemann sums, or some people say Riemann sums. I don't know. I guess it's up for interpretation. So Riemann sums, but this time in the case of integrating in two variables. So what we're going to do here is actually use small rectangles to divide this big rectangle. Okay. So we're going to kind of proportion it. So what we do here is now create our subintervals. So remember, okay, I'm going to go backtrack a little bit. And remember in the one-dimensional case, when we would have some f of x, right? And then from a to b, for Riemann sums, we would divide our interval from a to b into small little ones, right? So we're going to kind of do the same thing here. Let's say I'll just make it 3 big subintervals just for visual purposes. And then, but also, we have to divide the y interval as well. So I'll just make that into 3 as well. So we'll have something looking like this, like that. And then the lines extend up. Okay, I don't know if you can see that. The lines extend up and down. So we basically just divided this into 9 little boxes, or 9 little rectangles, okay? So then what you would do here, what this would look like on this graph, is that if we made divisions and cut through the rectangle, like that, and then similarly like this, right? So now we have little rectangles, okay? And now we have to use either, well, the problem will give you either like upper left corners of all these boxes, so then you'll have dots here, or, and similarly here, 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 or they'll give you upper right, or they'll give you midpoint. It just depends. But the important thing is the concept behind this. So what we'll have, let's say they choose midpoint. Okay, so then you'll be picking points right smack in the middle of all these little rectangles. Okay, and hopefully they don't give you too many divisions to make. Here we have 9 little rectangles, but hopefully they'll only give you 6 or so. So what this would look like on the graph on the left here is we're going to take these points, these little midpoints of the rectangles, and what we do is evaluate our f of x, y at these points. Okay, so let's say, well, okay, I'll just go over the general concepts here, and then I'm going to go over an example of it. So, yeah, well, okay. So at each of these points, we're going to evaluate our f of xy, which could be, I'll just keep using this example, x times y, right? So then you would take those points, your x and y coordinates, and then evaluate that point. So that would be like up here or something. And then what this essentially does is makes a very tall rectangular box. Okay, so this is, I'm just looking at the very left one here. It's kind of hard to depict on the screen, but if you can kind of see it, that would be great. Okay, so there's a rectangular box here, and you would do that for each of your 9 boxes. Okay, and then eventually that would just give you something that's an estimate of your volume under the carpet, or under the surface, when you're integrating it over your domain, which is determined by x and y intervals. Okay? So, let's see. Now you could, well, another side note, just when you're dealing with rectangles, so with rectangles, our domain D is sometimes called R. Okay, just for future reference, if you see it in problems and stuff, that's what it means, is R is just your domain, but it's the simplest kind, which is a rectangle. Okay? So, and head again into
on and carry on and fall all over the place.